These are the frequently asked questions for section 1-2, day 3. Somebody had asked about number 28, and so I'm going to go back and do that one first before I move on into the truly 1-2, day 3 material. In exercises 25 through 28, state whether each labeled point identifies a local minimum, a local maximum, or neither, and then identify intervals on which the function is decreasing and increasing. So the labeled points on number 28 are these 4 points right here. And it said, does it identify a local minimum, a local max, or neither? So I'm just going to list them off from left to right so that I can answer their questions. So -1, 1, if I'm looking at this portion of the graph, that is definitely a local minimum. And then 1, 6, as you look at it, we take a look at it and say, well, that's at the top. I mean, if we're looking for some region, some interval right there, that would be the maximum. And then 3, 1, again, if we're just looking at a certain portion of the graph, that would be the lowest point for an interval such as I've drawn right there. So that would be a local minimum. And we definitely could get 5, 4 to be a local max. All right, so that takes care of the first part of the question, which was whether it's labeled as a local minimum, a local maximum, or neither. So we have 2 of the local maxes and 2 local mins. Now what we want to do is talk about those intervals where they are decreasing and increasing. So what you really want to do is kind of think of tracing what you're seeing here and what's going on. So from left to right, this is definitely decreasing. We can feel that that is going down. Now, because there is no other graph to the left of this or nothing more that they can give us, we have to assume that that is really all that there is to this graph. So technically this is all the way to -infinity for this graph, since it's all that we get to see. And that's going to go to the point that we have right here, which is at this -1, 1. But what we're talking about right now is where it's decreasing over an interval, and those intervals always depend on x. So our x value here will be -1. So this is decreasing, and we'll have a increasing over here as well, because that's what's happening with the next portion of the graph. As I go from -1 up to +1, it is definitely increasing from -1 to 1. And then I would look at the portion of the graph from 3, 1 on down, and I see when or not from 3, 1, I should say this portion of the graph down to 3, 1. And that definitely is decreasing. So I think about, well, where is that at? Well, remember, these 2 are lining up right here. So that would be from 1 down 2, and then we are going to be moving to an x value of 3 that would be decreasing. And again, I know when you looked at the answers, you probably saw some closed brackets, but as we talked about in class, we are going to just use open brackets whenever we are talking about an interval, and that was an interesting way for me to spell increasing. All right, now from 3, 1 to 5, 4, we are increasing again. So that was from 3 up to 5 with the x values. And then we have one more downward motion, and that will be from 5 to, again, we have to put infinity because we are unaware if that's the rest of the graph or if there's more to come. So we would say that that goes from 5 to infinity. So those would be the local mins, local max, and increasing and decreasing intervals for number 28. Then 47 through 54, it says state whether we have an odd, even, or neither, and support it graphically, confirm it algebraically. So with 47, we have 2x to the fourth. And rather than try to put my TI simulator up here, which slows everything down greatly, I'm just going to go ahead and show you what that 2x to the fourth would look like just by drawing it. What we shouldn't have to do is think too much about what the quartic is going to look like. And that's because we know that they're going to be parabolic in nature. But if you plug this in your calculator, very quickly you're going to see a parabola like that. Now, what do you do next? Well, it says state whether it's odd, even, or neither. Odd means that it has symmetry with the origin. So if that were true, we would see a portion over here that would match this. And that's not what we see. What we see is the fold-over line appears to be the y-axis in order to get those two sides to be symmetric. So that's even. That is even. And then supporting graphically would be just show the visual, show me a graph of what you saw. Confirm algebraically would mean that we believe this, that f of negative x equals f of x. Well, what we need to do is we need to take f of x and we need to plug a negative into that function. And then realize that negative or positive of anything to the fourth power is still going to be positive. And that absolutely verifies what we found, because 2x to the fourth does equal f of x. We put a negative in it, it didn't make any changes to it, and that's what verifies that we have a function that is even. Number 53. Again, you might want to just grab a graphing calculator real quick. Although we do see this as a cubic, the visual often will help you figure out exactly what it is that you need to answer for these. So, like I said, I'm going to go ahead and just punch this in real quick and then get it up there for you as a sketch rather than using that TI simulator, which seems to slow everything down. All right, so expected a cubic, and this cubic is doing something like this. Like so. So the question becomes, are we talking about even, odd, or neither? Well, pretty obviously that's not even. However, odd, yeah, we might have some symmetry here around the origin, because if we took this and rotated it down here, this looks like it would be a perfect match. But to verify that, I'm going to go ahead and put odd for now. To verify that, I need to see g of negative x and see what happens. So what I do is I take that 2x to the third minus 3x and I put in a negative x in replacement for any of the x's that we see. And then we need to check the sign. The smartboard is writing about a half a second behind me, so it's getting messy. So g of negative x, if we raise anything that's negative to the third power, it's going to be negative. And what we have to do is compare that to the original, because if this is odd, what we just had has to be the same as negative g of x. So we go back to g of x and we see that it was 2x to the third minus 3x, and we're going to multiply that by a negative 1. And sure enough, it is negative 2x to the third plus 3x. So that verifies that this is odd. So again, even when we put that through that algebraic test, comes out to look exactly like the original, but odd when we put it in the algebra test, it comes out exactly the opposite of whatever the function originally was. So now, let me do a little erase in here and look at number 54. 54 is our parent function for hyperbolas. And it looks like so. And so at this point, I'm hoping you're looking at that and thinking, well, it's not even. I mean, it's not going to reflect over the y-axis, but it sure does look odd, which means we're reflecting that over the origin there. You can think of it as a turn, too. It'll work either way, 180-degree turn. So now, if it's odd, what we want to check out is h of negative x and see what we get. Well, that'll be 1 over negative x, which is 1 over negative x, just dropping the parentheses. So then we think, okay, if this is odd, that's supposed to equal the negative of the entire function, which it absolutely does. And so we did get a negative of the original function when we put in a negative for x. So that one was number 54. Next up, yeah, you probably already figured out how to do these by this time because we had talked about this in class today, but just in case. Number 55 is f of x equals x over x minus 1. And it just says use the method of your choice to find all the horizontal and vertical asymptotes of the function. So what we want to do is think, first of all, what would make that denominator 0, and that's going to be a 1. So x can't be 1. That means that is our vertical asymptote at x equals 1. Now, what we want to think of is what I was talking about in class, which is what happens if we replace that x that we see with infinity. Well, if we replace infinity with infinity, remember this minus 1 down here, that's our spitting in the ocean. That isn't going to do anything to this. Infinity will cancel out with infinity, and we will just be left with the coefficients, which would be 1 over 1, which means y equals 1 is our horizontal asymptote. And is that all they wanted? That is all they wanted. So x equals 1 for the vertical asymptote, and y equals 1 for the horizontal asymptote. Then, number 56, x minus 1 over x for g of x. Now, pretty obviously, x can't equal 0, so that's going to be our vertical asymptote at x equals 0 because it makes that denominator equal to 0. And again, think about this as infinity minus 1 over infinity. Well, infinity minus 1, subtracting 1 is not going to do anything to change the fact that that's infinity. So we really will have 1 over 1 remaining here, and that'll be y equals 1 over 1. So horizontal asymptote is y equals 1 for number 56. Then number 58. 58 is, oh, it looks more like a q, doesn't it? Q of x equals 1.5 to the x power. So with this one a little bit different. What you might want to do with this one is graph it to take a peek at it, although this is exponential growth. Hopefully you remembered that, but what we see here is that we're never going to reach that x-axis. So graphically, this one is a little bit easier to do. You know, we don't necessarily see all the things that we were looking for in hyperbola, so we should really take a peek at this one graphically to understand what's going on. So we notice there are never going to be any x values that we cannot use in this. We could keep going both ways forever. So it is continuous over the real numbers. So there is no vertical asymptote, but a horizontal asymptote, absolutely. We can see here that that's going to be y equals 0. We are never going to reach that. You can think of this fraction 1.5 as 3 halves to the x, and as we increase that negative power, we're just going to get smaller and smaller fractions, and so we never will cross that asymptote. And then number 61. Oh, this is a good one because this is going to require that you remember how to factor the difference of two cubes. So on the top we have a 4 that we can factor out. So I shouldn't just leave that notation behind. And on the bottom we would want to see, how do you factor x cubed minus 8? So you had to remember our little formula, since that's a minus. It'll be a minus b times a squared plus ab plus b squared when we factor that. and A is x and B is 2. So this will be x minus 2 times x squared plus 2x plus 4. And now we get a good look at, any of the zeros that we would be able to find. And in number 58, after taking a peek at not 58, this one is 61. Taking a look at the factored form that we have here, we want to figure out the vertical asymptote. So I notice 2 would be bad down here. It would make that equal to 0. But then we think, well, what about this one? Well, with that one, you might want to do just a quick little check of b squared minus 4ac. It's going to come out to be negative. Those are going to be imaginary zeros over there. Or you could say, you know what? I really like completing the square. I think I'm just going to give this a quick try and take 2 divided by 2 and square it, and that will add 1 to both sides, and that will give me x plus 1 squared equals negative 3, and I'll take the square root, and that's where you see imaginary, so we're not going to get any more asymptotes out of that one. And then you need to think about putting infinity in this, going to the right forever. So 4 times infinity minus 4 over infinity cubed minus 8. Well, what you see here, we don't care about the minus 4 or the minus 8. That's going to be spitting in the ocean. And so will this 4, really, because we're talking about infinity cubed in the denominator. So we're really saying this is going to be 1 over infinity squared. Well, that's going to get smaller and smaller and smaller, so close that we can't tell the difference between it and 0. So that gives us the horizontal asymptote of y equals 0. So that was an interesting problem. We haven't had to do the difference of 2 cubes pattern in a little bit, so that one probably messed with your head a little bit. And then number 73, this one is asking us to answer it without a calculator. And really, it'd be kind of silly to try anyway, because you'd have to come up with your own set of numbers, and hopefully you would figure it out by that time. 73 says, which function is continuous? So when I think about continuous, what I'm looking for is something that will never take a jump. It won't go from one spot to the next automatically, or because of a change in policy. So A says number of children enrolled in a particular school is a function of time. You're going to have jumps. I mean, pardon me, students leave the district, students come in, that's going to be a jump. B, outdoor temperature is a function of time. Well, from 1 second to the next, can we have a change in temperature that would be a drop? Probably 1 second. But when you think about it as a continuous thing, that's what temperature is. I mean, it just continues to drop or it continues to increase. So this would be best guess right now, but we need to read through all of these. Cost of U.S. postage as a function of the weight of the letter. No, they increase postage whenever they have to. There's going to be a jump, so that's out. Price of stock as a function of time. Yeah, unfortunately, there's some jumps in that, so that's out. Number of soft drinks sold at a ballpark as a function of outdoor temperature. Gets hotter out, going to be a lot more soft drinks sold, so that would be a jump. It all depends on the temperature. So B would be our best answer. It isn't a fraction of a second change. It is a gradual change over time. At least we hope it's gradual. And then number 75 for this one, decreasing functions. Which function is decreasing? So what we're looking for is one thing that goes up as another thing goes down. Outdoor temperature as a function of time. Well, not guaranteed. You know, we might be thinking about in Minnesota if you talk about at night, but this is outdoor temperature as a function of time. It's not always constantly going to be going down. B, the Dow Jones Industrial Average as a function of time. No, that's stocks, bonds, and that kind of thing, and that doesn't always go down. Air pressure in Earth's atmosphere is a function of altitude. Well, that's as they go higher, where the altitude is increasing. I was looking for the word there. The air pressure is dropping, so this would be our best answer right now, but let's read the other two just to see. World population since 1900 as a function of time? No, our population keeps increasing. E, water pressure in the ocean as a function of depth. So this one, yeah, you might have thought this one was decreasing, but here's what they're saying. As you go further and further, deeper and deeper, you're getting more and more negative numbers. And so it's really negative and negative in that one. So our answer is going to be C. Air pressure in the Earth's atmosphere is a function of altitude. That's why they say the air is thin up here, and it makes it harder to breathe. And that was it for 1-2, day 3.